Hey everyone, welcome back to my YouTube channel. You are watching Build AI with Sandeep. Previously, we have discussed all the components of the encoder and the decoder block, and we are at the final step of the transformer architecture. We are going to understand linear plus softmax layer, these two. So, we will discuss today what these two layers are, what actually they are doing, how they are doing. So, I will explain step by step what is these two layers. Okay, but before jumping to the today's topic, I want to take you in the start that we have our input sequence. Our input sequence is cat, drink, milk. Okay, so in encoder as well as in decoder, what we did, what we did basically, we made a vocabulary list, vocabulary list that have all the unique words of our training data. Okay, and we assign each word a unique token ID. We take index where these words came in this list and we assign. So let's suppose here 2 for cat, 2 is coming on second index in our vocabulary list. So we assign a token ID of 2 to cat. Similarly, we gave 5 to drink and 10 to milk. Okay. So after that, we create embedding vector. We convert our milk, our cat drink milk, each word into the vector. Okay. So I want to give you an idea that these two layers are doing the same but in reverse manner. So basically decoder gives us three vectors or four vectors, and we are trying to convert these vectors into words using these two layers, linear plus softmax. Now let's move to the next slide to understand how. So yes, this is our decoder, and we already know that what is inside this decoder block. There is mass self attention, cross attention, feed forward network, and we already know what they are doing. So after decoder has processed our input sequence, and here what is our input sequence? Our input sequence is start, cat, drink, milk. This is our input sequence that we gave to our decoder, and then after processing, decoder returns us these 4h. And what are all h's are vectors, okay, that have the information of each word. Okay, now we are trying to convert these vectors into words using linear plus softmax layer. Okay, and here these are, for example, for teaching purpose, I took these four vectors h1, h2, h3, h4. All have dimension 3. So h1 predict next word after start. Yes. So we are trying to achieve when we when we give start as input token to the decoder, we want next token in return. What will be the next token? Similarly, for other input tokens, we want next token in our output. Okay. So yes. So first we apply linear layer. Linear layer. This is a kind of neural network, and previously I already explained you about linear layer, but let me tell you again that what linear layer is doing. So before before going to the linear layer, we already know what is vocabulary, and in our case, I took this list. I make a list of I make a vocabulary list that have four words: cat, drink, milk, and. Okay, but in real life, there are billions of words, millions of words in the vocabulary, and they have their indexes uh, within the list. So, this is the one thing. Now, I will relate how this vocabulary is important for our linear layer. Okay, so let's understand. Till now, till H1, our vectors are of size 3. But as you can see here above, after we applied linear layer, vector size will become 4. Now why 4? Because our vocabulary have 4 words. That is why the dimension of the output of linear layer is 4. And each word is representing a score. Each word is representing a score of respective word in our vocabulary list. For example, here 2.4 is the score for cat word, point 0.6 is for drink word, minus point 0.3 is for milk word. Similarly, for and is it is minus 1.2. If in our vocabulary there are 1,000 words, if in our vocabulary there are 1,000 words, then what will be the dimension? What is the dimension of our output vector of linear layer? It will be 1 into 1,000. There will be 1,000 values, and that represent the score of their respective word in our vocabulary list. Okay, now you are understanding what is happening inside the linear layer. Basically, we are projecting our vector, our output of decoder, our vector to a new dimensional space. And how we are projecting. So let me take you back to the last slide. So here in linear layer, what is happening in linear layer, this dot product operation is basically done. Wx plus p. Now here what is x? X is basically our this matrix. This is our X matrix, and and its dimension is 4 cross 3. 4 is basically representing number of tokens, and 3 is vector size of each input token. Okay, so we will multiply weight matrix, and what will be the size of our weight matrix here? Our weight matrix is of size is of size. First, we will take what we will take vector size, our dimension, vector size. So our vector size is 3 cross. What will be the vocabulary size? In our case, vocabulary size is 4. When we multiply it with our 4 into 3 x matrix, x dot product w, then it will return 3 got cancelled out, and it will return 4 into 4 matrix. And each row represent each output vector of the linear layer. After that, we will apply a bias. We will apply a bias and x dot w plus b. So 4 cross 4 matrix will apply a bias here. Okay. So bias is basically again random weights we can say, and this w and b will uh, these W and B matrix have values, and these will be adjusted during back propagation, during training. Okay. So when we do the dot product, okay, when we do the dot product Wx plus B, this will give us 4 into 4 matrix, and each row represent the input, each row represent uh, the our output tokens. Okay. So these 4 vectors we will get from the linear layer. So now linear layer, what linear layer did? Linear layer outputs a vector of logits. We can say these values logit or row scores, where each scalar value represent the row score of one vocabulary word. Understand? Each row is one decoder position, each column one vocabulary word. So here I already explained that each value is representing the score of vocabulary word, one vocabulary word. Okay, and we will get these four output vectors from the linear layer, and these are called logics. These are row scores, not probability. Values can be negative or positive. Now we understood about the linear layer. Now the next layer is softmax layer. So why there is a need of softmax layer? As you can see, these are row scores. These are not probability. And when we sum up all the values, these values, it is not equal to 1. These are not probabilities. And the next thing is values can be negative or positive. So it is hard to interpret. It is hard to interpret. So for each word in our vocabulary, we need probabilities. What we need? Probabilities. That cat word is have probability of 93% that it will be the next word. Drink word is have X probability, X% of probability that it will be the next word. So we need probabilities. So that is why we are applying softmax on top of it, on top of linear layer. Okay. So for each row, we are applying softmax function, and we already seen softmax multiple times in our transformer series. So when we apply softmax function, so to to clear the confusion, so that you all does not have any confusion, I take position 3. Okay, h3. For h3 I will calculate the softmax values for this vector, and then we will get our final vector, softmax of h3. Okay, so for that we all know that what is the formula of softmax: exponential of xi divided by summation of exponential of xi. Okay, and we will calculate for each value, we will calculate the exponent similarly, and then for summation, for denominator is same all the time. This is our summation. And for cat word we calculate the probability 0.01, for drink word we calculate the 0.06, similarly for other positions. And finally we will get our softmax of h3, softmax of position 3. We will get this probability vector. These are probability, these are proper probabilities, and they add up to 1. So for position 3, the highest probability is 0.91. And what is the word at position 3 in our vocabulary list? In position 3 there is a milk word. Okay, so at position 3, it will return us milk. This is our next token. Okay. Yes. So as you can see, all the positions, you can see the highest probability word in our vocabulary. And softmax need one score per class. Each word is a separate class. Okay. When AND is generated, decoder stops decoding. Okay. So in this way, we succeed in our mission to get the next word. Okay, cat, drink, milk, and this is the output. This is the output. So we train our transformer architecture like this way, that we provide input sequence, and in case of decoder we shift our input sequence to the right, and first we give start as a special token. Okay, so start, and start gives us cat, drink, milk, and so yeah, this is the whole concept of linear layer and softmax layer. Now before moving ahead, let me clarify one thing. Let me, before wrapping up this video, let me clarify one thing so that there is no confusion. So the same linear layer is applied to all decoder positions. These are, these all are not, are identical, not different linear layer. There is a single linear layer, and we are doing dot product so that whole process is parallel. Okay, so why there is a only one linear layer having same weights and bias, those are trained. So why at every position there could be multiple linear layers? So because there are three reasons. The first one is language rules are position independent. Okay. So let's suppose we have a sequence, we have a long sequence and milk word is coming three times. First milk word is at fifth index, then again milk word is at 10th index, and then 50th index. So for each milk word, there is a different linear layer that could create a problem. That is a problem because milk is a same word. It is a same noun. It should be same. So how do we get to know that this linear layer is applied on the milk layer? So basically, linear layer gives us a universal mapping of each word in our vocabulary. Okay. The second reason is sequence length. There is a our sequence length must vary. Okay. It is not necessary that each sequence length is same. So when the sequence length varies, okay, then how do we know that how many linear layers we need? Okay, so this is again a big problem. And positional information is already inside the vectors. In the start of decoder, we already add positional embedding and it have the positional information. So why there are different linear layers? So this is a big confusion, and many YouTubers don't uh, don't tell you that there are single linear layer or multiple linear layers. So I'm telling you that linear layer is one, and all vector pass through the same linear layer and return us the vector, and vectors size is same as the vocabulary, and values inside these vectors are the row scores. And after that, to convert row scores into the probabilities, we are applying softmax function, and that will give us the next word. So same way, different input vector but different outputs also. So yes, this completes our today's concept, and in the next video we will discuss something called cross entropy. We will calculate the loss. Now I want to tell you that we take drink, cat drink milk, each word that we want in the output. But when we do training, it is not necessary that every time our model will predict correct next word. Okay. When we train our model, it is not necessary that each time our model will predict next correct word. So for that, we will compute loss, and we will do back propagation to adjust these weights or biases that we took in our encoder and decoder block. So we will discuss in our next video that what is that loss, how do we calculate loss, and how do we back propagate through the transformer architecture. So yeah, that is all for today, and I will see you in my next video. And if this video is helpful, then please do like, share, and subscribe, and share with your AI friends. And I need your support to make more helpful videos. I am planning that in future we are going to master Gen AI field. And yeah, thank you so much. Thanks for watching.